Alright, the first step to resolving a complex vector is to start using the parallelogram method. So I'll start making some dots here to create a parallelogram around these resultant vectors in both the x-axis and the y-axis. And once I have those, then I can draw a y-axis vector for this resultant vector and another y-axis vector for this resultant vector. Because it's on graph paper, it makes it pretty easy that I can just simply count the number of boxes. So here I have plus 9 newtons, and here I have negative 9 newtons, and it's negative because it's below the x-axis. I'm going to do the same thing in the x-axis. I'm going to draw the x-ness of this resultant vector, and that is negative 3 because it's to the left of the origin. And then I'll draw the x-ness of this resultant vector, and it is negative 7 because it's to the left of the origin. Once I have all this information, now I can start figuring out net forces in both axes. Now, force net in the x-axis equals all the forces, in this case going to the left, plus all the forces going to the right. Now this is where your negatives and positive signs become really important. You'll notice that I start with negative 7, and then I'm going to subtract 3 from that because they're both going to the left, and then I'm going to add 10 because it's going in a positive direction. When I do the math and figure out net, I find that that results in 0, and let's add a unit, newtons. So I've resolved the x-axis, and now it's time to resolve the y. So I'm going to switch to blue, and net force equals all the forces going up plus all the forces going down. Once again, positives and negatives apply. So force net equals, I'm just going to start with positive 9. And I'm going to add negative 9. When I solve, I get the force net in the y-axis to equal 0, and once again newtons. Now because the force in the x-axis is 0 and the force in the y-axis is 0, I get to say that this set of vectors is in equilibrium. In other words, there is no resultant.